Let's work on these examples of hydration the alkenes using the mercuric salts. So generally, you know that the hydration of the alkenes can be achieved by simply using diluted sulfuric acid, and in that case the hydroxyl group, the OH, is going to the more substituted part of the alkene. So this is more substituted, so that's the Markovnikov'r position, and this is the anti-Markovnikov'r position because that's less substituted. But sometimes instead of simply using the sulfuric acid, we're using the mercuric salt, and this is called the Oxymercuration Demercuration. So in the first step we have the addition of the salt, and then in the second step we use the sodium borohydride to get to the final product. And so the way this works is that in the first step we're going to make a cyclic intermediate in this position where this is connected to the mercury. So this is going to be our mercury, and that's going to be positively charged. So this is still connected to one acetate ion, and because of these two carbons also have partial positive charges. So after this tricyclic intermediate is formed, then we have the addition of the nucleophile. So in this case, if you run the reaction in water, water is the nucleophile, and it's going to do an addition using its lone pairs by attacking the more substituted carbon. And so the reason of this regioselectivity is that when the attack happening, we have partially broken bonds here. So if this is partially broken, then we have a secondary carbocation, while on the other hand, if this is partially broken, then we're getting a primary carbocation. So in the first case, secondary carbocation is more stable. That's why the water is attacking the more stable, the more substituted part of the tricyclic member here. And so the result of this is going to have the hydroxide on the more substituted part of the double bond. So this is going to be Markovnikov'r addition, and it's the same as we would get if we use the sulfuric acid. So the question here might be, why do we use this instead of the sulfuric acid? And you want to remember that if we're using an acid with protonate double bond, we're getting to carbocation first. And this carbocation is possibly going a rearrangement reaction by hydride shift. So here if we have the move of this shift of this hydride, then because of the rearrangement we're going from a secondary to tertiary carbocation, and this is more stable. And once the tertiary carbocation is formed, the addition of the water is going to create the other regioisomer of our product. So this is not going to be the target if we were aiming to prepare this compound. So because we don't have a full carbocation forming when using the mercury salt, then we're avoiding the rearrangements, and this is the primary reason for doing the mercury salts for the hydration of the alkenes. Now the second part of this question is the stereochemistry of this addition. So when the mercury is adding to the double bond, there are two possibilities. The mercury can add either from this face of the double bond facing towards us, or it can add from the opposite face. And when that happens, you can represent these either being wedge lines here, or it's also possible to get the intermediate where the mercury is going to be dashed line. And if this is going to be a dashed line, then the water will be attacking from this side. If this is a wedge line, then the water is attacking from the opposite side. So that means that in the product we're going to get a mixture where the hydroxide is going to be either a wedge line here, or it can also be a dashed line. And these two are mirror images, non-superimposable, so these two are enantiomers. Now this will only happen if after the addition of the water we're creating a chiral center. So right here this is a chiral center, that's why we're getting two stereoisomers. If after the addition of the hydroxyl group we don't create any chiral centers, then there's no need to discuss the stereochemistry, so it's just going to be one product.